Olli Mourujärvi and I work as a specialist at Lapland ELY Center, so same organization as Jaakko. And my topic today is impact of climate change on the road structures in the Arctic. It's a very wide topic, and I will concentrate on these issues today. There will be some general information about climate change and permafrost, and then one type of permafrost that we have here also in Finland, balsamires, and then at the end a few cases from Highway 21 in Finland. Most of the scientists believe that the climate change is real, and most of the people also, and I think so too. I'm not arguing against. It's causing rapid and unprecedented environmental changes in the Arctic, and I guess nobody knows what the future will be. There are many studies done and going on about the future, and there will be probably many surprises for road maintenance and designing. It has been noticed that the warming in the Arctic area is warmer than is faster than elsewhere on Earth, and the measurements show that the rate of temperature rise is twice higher than averagely on Earth. So it's bad news especially for permafrost areas. So the climate change increases the vulnerability of infrastructure because it enhances environmental stressors. So there will be more strains on the structures and that kind of strains that we haven't anticipated. Here are a few maps that show about the same thing that Jaakko was talking about. This is the change in mean annual air temperature. This map is here. I don't know if you see the laser pointer. This is from 1900 to 1940, and this is from 1940 to 1975, and this one is 1975 to 2000. So we can see that the change in the temperature has increased towards warmer. And these small maps here show the same time period from 75 to 2000, but it's different periods of a year. This one and this one are the winter months, and we can see that the increase in temperature is heavier in the north than in southern Europe. I was at the Winter Road Congress in Lahti in February, and there was Kerttu Kotakorpi, who is a meteorologist at the Finnish Broadcasting Company. And this slide and the next slide is from her presentation. He was talking about the weather in Finland at the end of this century, and she also said that the temperature will rise more than averagely on Earth, and it will be faster in northern Finland than in southern Finland. And the climate will change more in winter than summer. That was also we saw that also from the maps in the previous slide. At the end of the century, there will be more rain. There will be heavier rainstorms in spring and fall especially, and more snow in northern Finland and less in southern Finland. And this is very interesting that the climate in central Finland will be something between Poland and Hungary at the moment. So there will be a big change. This map shows the rise in winter temperatures, and as you can see, the rise is bigger in northern Finland, plus 8 degrees to today's temperatures, mean temperatures. And this map shows the increase in rainfall in winter time. So up to 40% in this part of Kainuu and eastern Lapland area, and less here in Turku, Pori regions. But this means that the amount of rainfall will be about the same as it is today in the United Kingdom. If you have been there, you maybe have noticed that it rains a lot. I found one study from 2016 which identified some of the stressors that the climate change will cause on roads. There is flooding, which will affect culverts and road and cause road washouts. And they studied also the adaptation approaches that we could do. So the conclusion was that the diameter of culverts and drainage system should be increased. And then permafrost thaw will cause cracking and subsidence, so settlements on the roads. And the base layer should be modified and install thermosymphons. There are many other ways also, and we will go to them later in the presentation. More precipitation will cause erosion and base layer damages, and freeze-thaw cycles, also base layer damages, cracking and rooting of roads. And here are two citations from studies. The first one is from Alaska, and it says that cumulative estimated expenses from climate-related damages to infrastructure without adaptation measures from 2015 to 2099 totals $5.5 billion only in Alaska. So it's a huge amount of money, and it will get very expensive. And the other citation from KUAC.org was that in a worst case scenario, thawing of permafrost would damage up to 3/4 of the roads, buildings, pipelines and other structures in the Russian Arctic by mid-century. So it doesn't look very good at the moment. Then some general things about permafrost. This is the definition approved by the International Permafrost Association. I didn't know that this kind of association also exists, but it says that ground, which means soil or rock and included ice and organic material that remains at or below 0 degrees of Celsius for at least 2 consecutive years. And it's particularly sensitive to climate change. Here's a map that shows where on Earth the permafrost is, and this line here is a border between so-called polar and mountainous permafrost. So south of the border, the permafrost is caused by mountains and high altitudes. And you can just think what it would look like if there was not this Gulf current here. Maybe this permafrost line could go through the central Finland. So we need to hope that this current will not change its magnitude or direction. Here are some pictures of the effects that permafrost thaw has already caused. This one is from Alaska, and you can see quite a big rift on the road shoulder. This is from Siberia. There is a landslide by one road, already threatening the road there. and this is from Alaska. The road has fallen down. And this is a natural roller coaster from Canada. This road is not in use anymore. So, how should we mitigate the effects of climate change on permafrost? There are some methods that try to tackle this issue, and some of them try to prevent the heat intake to permafrost. So they try to keep the air heat away from the permafrost. And some of them try to cool down the ground to get the heat away from permafrost. And of course there are also some reinforcement structures, for example geotextile reinforcements of embankments. These pictures are from one study also, and the picture A is insulation embedded along a railway, and this kind of polystyrene insulations have been used also in Finland and probably in many countries. So it tries to keep the heat away from permafrost in summer. But of course the negative side is that it also prevents the cooling down of permafrost in winter. So that's the negative side, but it's quite widely used. In picture B you can see sunset along a railway in China. It's very effective because it shades the sunlight away, and also it prevents the accumulation of snow on the shoulders of the railroad. So there is no snow, and it's not insulating in winter. So it's the cool air, or the cool air can cool down also the structures, so and the permafrost under the railroad. But the negative side is that it's very expensive, and it's not widely used. It's only used in some test sections at the moment. Then in picture C you can see this high albedo surfacing materials. So it's a coating on the pavement that reflects the heat away, the sun heat away from the surface. They are quite effective, but the bad thing is that they may make the road more slippery, and they are not probably so durable. So you have to repaint it or coat again in a few years. And it's not in the picture, but light-colored aggregates for asphalts have been used also in Finland. And the idea of that is that the heat absorption is not so big as it's for the dark aggregates. And these methods are to cool the structure down. This picture D is air convection embankment called shortly ACE, and this is in Fairbanks, Alaska. It's made of aggregates that are between 100 and 300 millimeters in grain size, and it can be used on the shoulders, and also somewhere it's used under the road as a layer. The effect is based on the voids that there are between the aggregates, so the air can flow inside the structure. And in summary, it cools down the structure in winter, and it insulates the heat away in summer. They are used quite widely. This picture E shows open air ducts which are through the embankment. This is from China, and these are not very widely used at the moment. There is a challenge that in winter you should block those. You should take the snow away from from the mouths of the pipe so that the cold air can flow through. And in summer you should block the mouths of the pipe so that the warm air wouldn't go inside. So this is not so good solution. And in picture F, it's you can see those pipes. They are for ventilation also, and these ones are inlets that the air goes inside, and these are outlets. The air comes out, and you cannot see there's under the shoulder there is a pipe going like this parallel to the road under the shoulder, and these pipes are ventilating it. So the cool air gets in, and then warmer air gets out. And these are mainly in test use at the moment. This is the newest solution in picture G. It's a kind of a sheet that conducts heat, and there is also ventilation pipes there. And this is under construction. It's the sheet is not visible when the construct is done. I don't know if yes you can see it here. The sheets can be positions differently in different kind of solutions. They can go under the whole embankment, or they can be only under the shoulders. And here you can see that there are also inlets and outlets for the ventilation. And this is only in test use at the moment. But in picture 8 you can see these thermosymphons, and these have been used for 40 years already. And the idea of them, there are these pipes that stand vertically on the railroad. There is inside there is usually carbon dioxide, or of course can be some other gas also, but it's in gas and it's also in liquid in the pipe, and the change in the from gas to liquid makes to pump the heat away from the embankment, so it cools down the embankment. And they really work, but of course not so cheap either. And here's a picture from Alaska. It's under construction. These are also thermosymphons, but on roads they should not be vertically standing by the road, because it's not good for traffic safety. So in Canada they have been testing this kind of a solution where they have V-shape thermosymphons. You can see now the upper side of the pipe, which will be right under the pavement. And in winter it cools down. It will be very cold when there is like minus 30, 40 degrees Celsius, and it pumps the heat away from permafrost. The other part of the thermosyphon is going very deeply to the permafrost. Okay, so then we will change to balsam wires, which we have here in Finland, and I guess also in Norway and northern Sweden also. The name balsa is from Sami and Finnish language, and it's at the moment it's internationally used. It's a large peat hammock which has a frozen core inside, and it rises above the ground. And they are local formations, not very big in area, and that's good news compared to the continuous permafrost, because you can make construct your road so that it doesn't hit these. But of course, somewhere in Finland, as we will see soon, it happens that the road is on the balsam wire. They can be up to 7 meters higher than the surrounding ground. And this map shows that they are not all circles. There are many shapes, and these circle, which are called dome shapes, they can be up to 150 meters in diameter. But these longitudinal pulses can be half kilometers long. There are quite many of them next to each other in this map. And this is from Utsjoki. So when can we have pulses? You need to have water, of course, and usually it's a wet mire. There has to be a peat surface more than 40 centimeters, so that in summer the peat is an insulation and the ice doesn't melt away during the summer. There has to be thin snow cover. It's either so that the place is so that there is not very much snowfall, or the place is above the ground by it. So the wind can blow the snow away, and the freezing goes deeper when there is no insulating snow. And the optimum mean annual temperature is between -3 and 5 Celsius. So we will not find these in Helsinki. It's only in northern parts of Lapland, in Finland. This shows the life cycle of balsamire. So the freeze in winter has to go deep enough so that in summer, when the melting happens, there will be a peat surface which insulates so that the ice doesn't melt away, and it starts to grow each year, of course slowly. The pulses at the moment are under 1,000 years old, so it's not in 10 years or 100 years. It needs to be more time for this formation. And finally, at some point, the balsa ice core gets so high that it starts to fall down, and when it's cracking and falling, the ice will start to melt away, and there will be only a little pond of water after that. And here's the map where these pulses can be found. This area is probably because of the mountains, I guess. Okay, then to Highway 21, which we will actually, I guess we will visit that. Aurora project is on Highway 21 here in is it here? Muonio is here, yeah.
Not the pulses.
No, this is not the pulses. Pulses are around here. So we will not go that north. But the current government in Finland decided to start two programs to reduce the maintenance backlog that we have in Finland. It's calculated that it's was it 2.5 billion euros. And from these programs we finally received funding for repair at least part of Highway 21. We got 30 million euros, which is not, of course, enough to build, to repair the whole road. But we decided to repair section from Kolari to Palojoensuu, and then these balsamires which locate close to Kilpisjärvi. The highway is too narrow, and the geometry is very poor at the moment, and there is up to 26% of heavy traffic and over 100 incidents of heavy traffic falling out of the road to the ditch. And as Jaakko already mentioned, it's an important road for example, for the Norwegian fish transports. So here you can see there's Kilpisjärvi, and here are these locations where the road is on the balsa balsamire. And this picture is from balsamire. So you can see that it's quite uneven because it has been settling every year. And the balsas are thawing probably because of the climate change, of course, and also the fact that the road has been built on the balsa. It has changed the natural conditions of that balsa. And the pavement is absorbing heat in summer, and it's warming up the structure and also the balsa, the frozen core of balsa in summertime. Because it has been repaired, the settlements have been repaired every year as a first aid. There is up to 1.6 meters of thick layer of pavement, or used to be, of course not anymore because this is now under construction, as we will see soon. So with this money that we got to Highway 21, we ordered some measurements for the balsa mires to find out how to fix the problem. There were some ground penetrating radar measurements, then electrically resistivity tomography measurements, and drillings. And the surprise was that there was clear ice under the road. It was, before the drillings, it was anticipated that the ice would not be clear, but it would be some bead that is frozen. But it was found that there was 4 meters thick layer of this clear ice at some positions of the balsa. These 3 balsas, Iitto, Saarikoski and Mourujärvi, were not so deep. There was only 6 meters of peat left, and actually all the ice had already melted away. So, but they were still settling every year. But it was possible to repair these locations by excavations, which were up to 6 meters deep and from 220 meters to 590 meters long. So not so long sections. And the repair was done last spring in April and May, and all the peat and frozen soil was taken away and then replaced with gravel and blast stones. And it was done this time of year, April and May, because the ground was frozen, and it was done 1 lane at a time. And the filling was proceeded right after the excavation, so that the excavation wouldn't collapse. And this is a picture of one of those places under construction. Okay, then we will go to the Speera balsa mire, which is about 18 kilometers south of Kilpisjärvi. The location looks like this on the map. There is a river and a lot of one lake and a lot of water. Also other balsas here and other mires. So it was decided that there will be not any kind of changing of the alignment, because it would have been quite a long alignment change also, and not cheap either. And probably also in this area it would have probably caused some challenges with the nature values if it had started to design the road in some other place. So it was decided to keep the highway at least its original position. Here you can see the GPR and ERT and drilling results in one picture. The ice is 4 meters below the road surface, and there is up to 4 meters thick layer of this ice. and the bedrock is from about 14 to 16 meters under the road surface. And it's only like 200 meters long section. The aim was, of course, to make a permanent solution. And many options were considered also at this point, and the decision was to construct a bridge and a continuous pile slab also. It was estimated that the bridge solution will pay back its cost, because it will improve the traffic fluency and safety, and there is no more need for the first aid repairs and to add the asphalt every year. Here's the model of the solution. On the melted section of the balsa, there is this continuous pile slab structure, which is about 58.1 meters long and 13.4 meters wide. And the bridge is 92.6 meters long. The slab has heat steel piles under it, and the size is 170 millimeters and 220 millimeters, and they are about 12 meters in length.
Why did you use steel piles?
Sorry?
Why steel piles and not concrete?
They are steel, but they have been cast inside.
Yeah, but why steel and not concrete?
I don't know that.
Yeah.
And the bridge has 14 drilled steel piles, which are 813 millimeters in diameter and about 14 meters in length. And the span between the supports of the bridge is only 15 meters, and this is because of the ice. If this was a water bridge, it would be longer span. And of course there was challenges in this design, because this has not been done, at least in Finland, on frozen balsa, and they had to think about the forces that the ice will cause for the piles, and they had to think about what will happen when the balsa has melted away. So just in case, there is a friction slab under the ground in the other end of the bridge, which prevents the horizontal movement of the bridge on this end, and this end is anchored to the pile slab, and all these piles are anchored to the bedrock, so that the ice will not start to lift the whole bridge up. And at the moment the bridge is there under casting. The casting started yesterday morning, and it's ongoing now at the moment, will be probably finished today afternoon. So over 24 hours of work, and the detour during the work is by the road in the ditch, and the soil under the ditch is now frozen, but it will melt soon. So there is a quite tight schedule to get the bridge on traffic during May before the detour will melt away.
And also there was a strike of concrete suppliers that will maybe start tomorrow, so we are in a hurry to do it before that.
So actually you're leaving tonight?
And the concrete will be transported from Kittilä, from here, and it's 250 kilometers in distance, and that of course is a challenge for the quality of the concrete, and also a challenge to find enough trucks, because there are not so many in this area. They will probably they probably have brought some from Rovaniemi and Oulu, maybe. I haven't heard, but that's what the project manager said before the casting, that it's a challenge. Okay, thank you.